Right, thanks everybody. We've got a few more people joining as we go, but for those who have already joined, welcome. Thank you for joining us today to discuss Plexus. We do have a poll on the right-hand side of your screen, and you can fill that out while we wait for a few more to join. There's also on the right-hand side, you'll find a chat log, and please feel free to let us know where you're dialing in from and to use the chat to ask questions throughout the webinar. We will have a dedicated question and answer session at the end of the webinar, but do post questions during as they come to mind, and I'll keep track of those and we'll get to them all at the end. If we don't get to your questions, one of our speakers will follow up with you after the webinar to make sure that it gets answered. So I think to give you an outline of the structure today, our speakers will share their thoughts for about half an hour or so, and then we'll wrap up with about 15 minutes of Q&A. There seems to be a wee drop off in the number of people joining now, so I think we might get underway. So welcome everybody to talk about Plexus today. We're living in a data-driven world, but we can ask, what is drive without direction? Today we're introducing Plexus. It's an end-to-end, real-time, high-volume data delivery package tailored to your needs. The amount of data out there can be overwhelming, and the range of data solutions might leave us with more questions than answers. But Plexus is built with your organisation in mind, allowing you to easily interpret data, integrate it with your current systems, and sharpen your insights for better informed decision making. It's not just the amount of data you gather, but it's what you do with it. Today we'll discuss how Plexus incorporates real-time data, 24/7 data, to produce a comprehensive picture. It is low cost, high value, and how it is fully scalable, and how Plexus can help you reduce risk and identify potential issues before they arise. I'm Penny Kneebone, Discipline Director for Natural Resources at Tonkin Taylor, and I'll be your facilitator for the webinar. Today we have with us three experts in water. First up, David Wiley. David is a Technical Director for Digital Innovation. He started his career as a civil engineer over 30 years ago, but he quickly moved into the digital space, working with all aspects of asset performance data. He was involved in some of the first hydraulic models for Thames Water in the UK, and this has allowed him to develop transformational modelling processes. He's here to take your asset data and turn it into actionable insights. Next up, Darren Wilson. Darren is a wastewater and stormwater engineer with over 25 years experience in modelling, analysis and analysing and planning urban pipe networks. He has a career-long interest in developing new tools to gain insight, improve predictions, reduce risk, and make better decisions. And third, we have Tony Cousins. As Tonkin Taylor's Sector Director for Water, Tony has the responsibility for developing a wide range of technically challenging water projects and consultancy services throughout New Zealand, Australia, and the Asia-Pacific region. These projects include civil, water resource and geotechnical engineering, dam engineering, environmental and planning services that combine the exceptional quality of project delivery, which consistently exceeds client expectations. We'll start off today with David. David.
Hi there. I was just going to quick run through of our agenda, and I really wanted to sort of obviously we're going to have Tony go through the three water reforms. We're going to have a little background on what we want to cover, traditional modelling approaches, talk about Plexus and what we've been doing on the data-driven modelling, and then talk about real-time modelling, and then maybe think about what happens next. Over to you there, Tony.
Okay, thanks, David. Look, I won't take up too much time around this because I know many of the listeners on the call today will be familiar with the reform process that we're involved in right now, but there are probably two or three aspects just worth touching on that provide a context for some of the discussions that David and Darren have this afternoon. So I guess we all know that central and local government embarked 3 years ago post Havelock North. That was clearly the catalyst for the reforms, but onto a program of extensively reviewing both the delivery and the regulatory structures for for water services delivery in New Zealand. Just looking at, they've gone into a very extensive program, and for those that have tracked this, that's not for reading there now, but really just illustrating that central government through DIA and local government have got extensively involved now in the detail of how the reform is going to roll out. There's a lot of information in behind it that supports some of the analyses and also gives direction to the timeframes. So on the legislative side, we've now got the water services, so Tamararawa establishment legislation and the water services legislation, which all sets the framework for regulatory and structural changes under the reforms. The second part is a focus on the underinvestment that we've seen in the Three Waters infrastructure in New Zealand that led to some of the problems that we've seen. And most recently, some of the Water Industry Commission for Scotland work, the WICS work for DIA, has concluded that there's $27 billion of additional revenue required for infrastructure and Three Waters reform in New Zealand. So, and also there are other reform components around resilience and climate change that the government are going to look to incorporate as well. So it's a very extensive reform. So given that, it would give us the great opportunity in that massive infrastructure spend to not only introduce new infrastructure, but also to get data management systems much better in place in support of that as well. Not least to get more improved data platforms, but also the fact that there's going to be regulatory structures, reporting structures, real-time monitoring and event-based monitoring that's going to be required as well. So it seems an ideal platform for significantly improving the data management component as we move into the infrastructure upgrades over the next 10 and 20 years. So that was all I had for now, and back over to you, Darren.
David, on this occasion. Oh, the bit that really interests me is we've seen over the last few years that the cost of collecting of data has dropped dramatically. You know, the cost of devices, cost of communication, battery life is extended immensely, which means that we're actually moving from this world where we have very little asset performance data, and the engineer's role is sort of filling in the gaps. And you can see that the future state is a place where we have sort of vast amounts of data, maybe more data than we can deal with, and we're already seeing that on occasions. And the engineer's role, or even some systems that are developed, is needed to sort of filter out what's important and what isn't, rather than fill in the gaps. It's figuring out from all this data we've got what really matters to us. And we're going to see this change exponentially over the next 2 or 3 years. Over to Darren to talk about the traditional modelling approach.
Thanks, David. Hydraulic models became a boon for the water industry about 30 years ago when they and desktop computing became more widely available after some significant industry and government investment in the field. However, at the time, computing power was limited, which often led to simplified models, both in network and hydrological models. Asset data was often poor, and the flow surveys which we needed to calibrate and understand how the networks were performing were a significant investment, so they could often only be afforded to do over short-term periods of 5 weeks or so. So it often ended up being a very snapshot picture of what was going on. And the old equipment had accuracy issues and was very maintenance intensive. And due to the vagaries of the weather, you didn't always get what you wanted. We then used these models to tell us how networks were really performing based on very limited data and often with a lot of information backfilled by assumption. That led to some gaps in knowledge and significant room for improvement. Over recent years, there has been significant improvement in these areas. As computing power has improved, so has model complexity. But that has not always come with an increase in the amount of data that we capture to aid that improvement in complexity. Flow surveys, the accuracy of the equipment has certainly improved, the reliability of the equipment has improved, and that's often come with some reduction in cost, meaning we can do surveys for longer periods, but it's still a significant portion of the total study cost. And that still leaves some significant gaps in our understanding of how things are progressing in the real world. Asset data availability is also improved, but there's still some significant issues. And we all know that environmental standards will keep improving and getting tighter, leading to more stringent consenting conditions. Public expectations of what we can achieve will only increase, and there's a need for better outcomes with carbon accounting and making sure we're making the right decisions and investing in the right projects. But this leaves us with models that can't always be extrapolated to the performance targets that we need to meet through a lack of data, either through the short-term flow surveys that we do not being fully representative of real conditions. They're based on a snapshot. Was it a dry year? Was it a wet year? How has that biased your data and your model and your decisions? Not observing crucial runoff or infiltration processes, basically how runoff and infiltration changes with extreme events, but also season to season. This often leads to gaps in our understanding of how the real world functions, and therefore models that cannot be reliably used for operational real-time control modeling. And we often find that we don't have the detail or the knowledge in the areas that we need it. Obviously, the cry of the industry is we need more data, we need longer periods of data, and we need better insights and a deeper understanding of how our systems are performing to improve the models we create and how we use them. And as we go forward, as new technology comes online, obviously the way we model and analyze them may also change over the coming years. So over to you, David.
On to Plexus, and the main reason for this presentation, I guess. I suppose it all started with a bit of a what if, you know? What if we could utilize all the SCADA data that's held within an organization? And what if we can utilize the traditional flow models and the new IoT devices I talked about earlier, you know, low-cost Internet of Things devices? Have the models built from the data rather than being these sort of offline activities that are really difficult to maintain. Maybe get models that improve over time rather than become out of date. Models that learn what normal looks like, so you can actually see things when they're not normal, you know, the anomalies. And models that get utilized both planning and operations. And you can then kind of have a sort of a data-driven model that really enhances your traditional modeling approach. You don't eliminate a modeling approach completely, but an awful lot of work could be done from the data itself. And the idea is you've got data coming in from IoT, SCADA, RFID, CCTV, etc., feeding in. You've got your basic network data coming from your GIS, and this gives you your performance data. And effectively, you're doing an analytics on it. You're looking at potential problems. You're looking at improvements. This data is feeding into your data-driven model that's giving a feed to your capital planning operations, which are all feeding back in. So you have this loop where the system gradually improves and data's available to all. So the question is, how do we really get there? Well, this is a high-level architecture diagram, so I'm not going to go into it too much detail, but we decided, well, let's try and use a cloud-based system. Let's start using data science style techniques rather than just engineers with spreadsheets to deal with data, and let's see what we can do. Can we deal with thousands of devices sending us data in real time? Can we QA that in real time and utilize it to understand how the system's working? What we got from initial insight. So basically we were working with Nelson City Council, taking the suite of tools, which is basically Plexus, and saying, okay, where do we start? At the beginning of it all, there wasn't there isn't thousands of devices sending real-time data. So we processed the SCADA data. So we took, on this occasion, we took 2 years worth of SCADA data and process it to say, well, what does it show us? And obviously at a high level, you can't see much here, but you can see there's lots of dropouts in the data. They've got about 18 pump stations. But what we did discover in that processing was that you could see your clear diurnal patterns as expected. You could see the impact of rainfall. You could actually then start to see what normal dry weather flow looks like. And we could also see the impact of tide. And in the lower parts of NCC, that tide is a significant factor. And you could see during the higher tides, which there aren't very many of, that there was significant infiltration in the system. But we could also then see during the lower tides, there's significant exfiltration as well, which I'd never seen before from traditional short-term flow surveys. Really, there isn't enough data. The fact we can actually pull 2 years worth of data and reliably use it for initial insights was fantastic. This gave us the ability to sort of initially understand, well, how is your network looking? So each of these diagrams shows the sort of the worse and the better based on the impact of storm. You can see the storm response, not the red ones, obviously a higher storm response, and yellow are the lowest. So you can then prioritize and decide where to look next, which gave us the opportunity to start looking, well, where do we go and put in these low-cost devices and flow monitoring devices to understand, well, what's really going on in these catchments. The same for tide, and you can see the areas, unsurprisingly, are those ones in the lower lying areas with significant inflow. We could then use that to create simple dashboards. So our clients can actually go in and drill in anywhere and see what's going on in their network. On this particular dashboard, it's showing you, quite interestingly, how much of your flow is coming from your dry weather flow, how much is rainfall, how much is tide and infiltration, which is a really useful way to look at things. But obviously, this is kind of a historical. This isn't live. This is a sort of a backward-looking thing, maybe telling you where to go next. And this has been used to give us great insight to decide, well, where do we start? Where do we start putting additional devices in? If we're going to go down this approach of a data-driven model, we need to actually figure out where do we put devices in. We could put devices in everywhere, which would be utterly expensive, or we can start in the important areas, which is what we're trying to do with Nelson. So we're now moving into this sort of real-time modeling approach. Basically, what we discovered, when I first thought about this, that we thought, oh, well, if we put devices everywhere, we'll have all this data and we'll be able to see what's going on. And what you actually end up with is lots of points of data, which is very nice, but it's not really telling you what's going on. So the first thing we had to do was actually understand how the network all joins together. So from the GIS, take the data and you've got connectivity, basically. We also had to figure out, well, where are your people? So to every pipe in the network, we've allocated all the people that contribute to it. And there's a diurnal pattern, and the system understands attenuation. So you have this sort of base flow of dry weather flow running through the system. On top of that, we can start adding other factors. And here you can actually see the dry weather flow profile. And obviously, some of those other factors being infiltration. So we then have to basically take this people dry flow and additionally add the water resulting from infiltration, which you can see significant component of the flow in some of these catchments, like Parapara, is infiltration. So that's then added to the base flow, which lifts it up. On top of that, we then have to thinking, okay, what are the things that are giving us the response we're seeing due to rain or due to tide? It could be groundwater, time of the day, time of the week, etc. So all of those pieces in, which then gives us a tool which is able to start taking feeds from predicted weather to tell us what's going to happen next. But what we found, interesting enough, is as you looked into this data, you get all sorts of interesting insights. When you start looking at the graph here, you see this is basically the response to rainfall, and you'd expect it to continue to keep going up as rainfall increases. But because we're using a model that doesn't really understand hydrology, it's showing you how the system responds. And what it's showing us through the system, even when your rainfall gets to a certain level and beyond that, the water just doesn't get in. or can't be transported due to pump capacity or something else. So you have a slightly different shape than you'd expect. What we also see, again, on the tide piece here, we see a huge response to the larger tides. During the sort of normal tides, there's very little impact, but on the low tides, we actually see a negative effect. Again, we see the exfiltration in detail, and that's all then in our model. Whereas with a traditional hydraulic model, we wouldn't have probably collected enough data to be able to have those insights. But number two, it would be nigh on impossible to actually deal with exfiltration, because we're looking at it on a pipe-by-pipe basis. What that has then allowed us to do is create a model that's derived from the data, can take real-time feeds and predict what's going to happen next. So what we're showing on a graphic here is on the left-hand side, everything in blue is what's been. Everything in yellow is what's predicted to be. And we've got then on the right, what in blue is the tide that has been and the tide that's predicted. And then we actually have here in the predicted rainfall in blue, and then the predicted rainfall. So what we can see from that is the future flows based on change in tide and rainfall. And the system already understands what's happening in terms of your dry weather flow. So it'll already know when this hits, how much impact that will have on the network. So if it's during peak dry, sort of peak in the morning or peak in the afternoon, you get a different effect from other times of the day. The future. This gets kind of interesting. You know, we move, as I said earlier, we're going to see so much more data that we're not going to be able to do what we used to do. We're not going to have a bunch of engineers doing things in Excel. We need to be able to get real value out of all this data that we've got. We found in the case of Nelson, it was massively useful to give us a starting point. If we go down a route of purely data-driven models, you don't want to wait years to have enough data. You may well already have enough data sitting in your systems. You've just been unable to mine that effectively with traditional engineering approach. We want to see answers more quickly. So this data we want to see in real time. We will, if we get this right, this will create true digital twins. They are derived from the data on how the asset's performing. They stay maintained, and they give you huge insights. We're going to likely to see a whole pile of movement towards quality modeling. We're going to have effects-based stuff going on with IoT involved with this, you know, with devices out actually looking at what's going on in the watercourses and what's really going on. And we're probably going to want to have to build less and get more out of the existing systems. So with the use of more data and real-time modeling, we actually set ourselves up beautifully for real-time control of our network. So we can actually start to basically utilize the capacity that's available in real time and eliminate some of our flooding or overflow problems before they actually occur without building huge amounts of infrastructure. And at that point, I think we're ready for Q&A.
Great, thanks, David. We've, for those who joined later and anyone who's had questions come to mind during the presentation, please feel free to use that, or please do use that chat box on the right-hand side of your screen to post your questions. We've got a couple of questions there which we'll come to. We also had a couple of polls running when you joined, and just to give you, you might be interested in the outcome of those if you didn't keep track of those polls. The first question was around, are my hydraulic models meeting my needs? And we had about half of people said sometimes, about a third said never. So there's clearly some room for something different in this area, which is great. And the second poll was around how often do we update are we updating our models? And about half of respondents said more than 5 yearly. So some interesting results there in the polls. And I think there's a third poll coming, so keep an eye on that poll box there. In the questions, we had a question from Clint Cantrell, and David, this might be one for you. Are there non-three waters industries and utilities where we can look at as examples of where Internet of Things has been leveraged and benefits have been realised? Want to speak to that one, David?
Yeah, and I think that's really interesting, and I think other sectors have been quicker to pick this up. I think most sectors are still struggling to deal with the data. It's been a real problem, and you know, I mean, you see examples of industries where they're putting lots of sensors in, you know, whether it's air quality or whether it's inside factories for management of machineries, or you know, plant companies doing it so they can keep what's going on. So yes, there's a huge amount to learn from it. I think what's interesting, or the piece that really interests me in what we've been doing, is trying to actually not just look at each of these devices in isolation, but say, how do we understand how they work together as a whole, you know, as a network? And that was the most interesting part, because it's actually surprisingly easy to just try and understand one little point in space, but actually trying to understand how all these points join together is decidedly complicated. So yes, we can always learn from others.
Great, thanks. Good stuff. And there's a follow-up question from Clint, which might also be you, David, which is around any information out there available about investment versus beneficial paybacks and investment decision-making and operations and maintenance efficiency. Is that something you can speak to?
Thanks for that question, Clint. I'm sure there are, and actually, and I know there are, and I can't put my fingers on it, but yes, where we've I've been involved in projects in a lot of places, actually, with Clint, as it happens, where you have tried to look at trying to get better value out of your assets rather than just building new stuff. And a lot of the time, the problem is we really don't fully understand, or even worse, we think we understand. And you know, coming from a modeling perspective, there were a lot of sucking of thumbs and guesswork goes into making a model do what it's meant to do, but we're tying it to such a small set of data. You know, if we're lucky, we've got a few good storms and a few dry days that we've calibrated to, and then suddenly we're putting these events onto it, you know, 1 in 100-year events, and saying, oh, that's going to be great and that's what's going to happen, and then investing millions of dollars on it. And I think a solution where we are much more confident in the data, this is learning from how the system's really behaving, will give us much more confidence in making decisions to really utilize the available capacity in a much smarter way through real-time control. And specifically, as answering Clint, making something like Lima that really works properly.
Great, thanks, David. We have one more question posted. Just another reminder, if you do have questions, please do post them and we'll get those answered here. But the final question from Tim, and again, David, this might be you again, or possibly Darren, we can jump to, that we seem to live in a design storm load paradigm, which focuses design for extreme events as a basis for capital investment. And Tim's question is, will these data-driven models replace that approach?
I think Darren should answer this.
Yeah, he's jumped in.
It's totally driven by what your consenting standards and levels of service you're trying to achieve are. I think certainly with the wastewater models, we tend to be moving towards using time series events to assess average performance or frequency of performance rather than extreme design events. I think that's the general direction the industry's going. Obviously, that requires good models, good data, and long periods of data to make sure that you're able to replicate the full range of flows your real system encounters. And I think what we're on the cusp here of moving from building a model to tell us what's happening and use that model to tell us how things are performing, to moving towards using the real system and real data to tell us what's happening and how it's performing.
Great. Thanks for that. Look, we don't have any other questions there. One last poll that you've filled out. Thanks for doing that, about whether you are using or planning to use Internet of Things devices in your Three Waters networks. And there's 2/3 of respondents are planning to do that. So clearly this is where things are now. Look, I'd just like to say thanks to everybody for joining us today. Thanks to our speakers for speaking, and thanks for the questions. Really appreciate that interaction. And we will be making this a recording of this webinar available to you. So look, thanks again, and we'll wrap up a little early. Thanks. Bye bye.